Up till now, we were dealing with reaction concerned with C double bond O. Before beginning the reactions, I told you there would be three kinds of reactions. The one that will deal only with carbon, the one that will deal with this pi bond, and the one that will deal with hydrogen at alpha position. Because of that hydrogen is acidic. So now we were dealing with C double bond O. There was addition, and the last reaction, last to last reaction, there was addition elimination. And after that we studied a rearrangement reaction, Beckmann's rearrangement. Now we are moving on to the kind of reaction that will deal with this hydrogen at the alpha position. Fine. Okay. So this reaction will be called as aldol condensation. Aldol. Ald for aldehyde and this ol for alcohol. We'll see in the final product of not the final, but the intermediate product of this reaction, you will have a compound having both the groups, aldehyde and alcohol. So that is called aldol. Right? So let's see what is this reaction all about. Suppose I take acetone and I added dilute KOH or NaOH, any convenient base, into the system having acetone. Now let's start discussing. You think, I'll tell you, you think more, then I'll tell you. Try to be ahead of me. Okay, so tighten yourself and let's start predicting what can happen. You have acetone in the system and you have a base in the system. You tell me what probably can happen. You have a base, fine. What does base do? There are two kinds of electron-rich species in organic chemistry. One is a base and one is a nucleophile. And long back we studied the difference between them. So I am telling you it's a base. So it's very convenient for you to think what it will do. Base abstracts proton. Nucleophile attacks a site which is electron deficient. That's the primary difference between a base and a nucleophile. Now I have used a base. KOH is a base. NaOH is a base. Now this base will do nothing but abstract proton. Will abstract H plus atom. H plus atom is nothing but a proton. Fine. Now there are two sites. Both the sites are alpha sites. Both the hydrogens, both the carbons on the sides, both sides are alpha carbon because both are directly attached to carbonyl group. Now all 6 hydrogen here are similar. So base can abstract any one of them, right? So the first step of the reaction would be base comes and abstracts one hydrogen. I'm glad you predicted that. Fine. So you develop a negative charge on this carbon from whom H plus has been abstracted, and this OH minus becomes stable molecule H2O. Fine. Now what you have done is you have developed a negative charge on carbon, and negative charge on carbon by no way is a stable because the carbon has small size and carbon do not have high electronegativity value. So this negative charge got to be stabilized. Now how will it be stabilized? One way to of temporary stabilization is resonance, of course, because this negative charge will undergo resonance with this C double bond O, and the charge is going to appear on this oxygen. If you shift this pi bond towards oxygen, this carbon will develop a positive charge, negative positive going to form a bond. So one of the resonating structure will look like this. That's okay. Because of resonance, the lifetime of this intermediate will increase, but it got to be stable somehow. It cannot remain charged for a long period of time. The resonance can only increase the lifetime of the intermediate. Resonance cannot make it so stable that it will exist as it is. Now that charge has to be dispensed somewhere, somehow. So, and when you have a charge on both carbon and oxygen, then the reacting side is carbon. because carbon, because of resonance, these two, in the resonance hybrid, there will be character of both the resonating structures and there will be charge on both the sides. For instance, this hybrid will look like this. Del minus here, del minus here. But for reaction, this site will go for reaction because this is the unstable site. Because negative charge on carbon is unstable. There's a negative charge on oxygen as well, but that will not go for reaction because you have a more unstable site to go for reaction. So carbon is the end at which the reaction will occur, not oxygen, although it carries negative charge. I have clarified that before, but just for quick recapitulation, carbon is going for reaction, although oxygen also have negative charge, but that's a stable site because oxygen is the second most electronegative element of the periodic table. So what's the way, how this negative charge can be dispensed? The negative charge, the one way that we have learned up till now to dispense the negative charge is to go and put it somewhere in some orbital, either bonding or anti-bonding. Now there is no plus charge around, so there is no bonding orbital empty. So in that case, the negative charge has to go to anti-bonding. And the source and one probable site, as you must have thought already, is this carbon of this acetone, because it has a del positive charge, because oxygen has pulled electron and has earned del negative charge. So what it will do is, there will be some unreacted acetone present that has not reacted yet. So this negative charge is going to come and put its electron into the orbital of this carbon. Fine. When that happens, this electron will move into the orbital of oxygen. Because carbon is making a new bond, it has to break one previous bond. So what happens, this carbon and this carbon forms a bond. And the intermediate will look like this. Fine. This carbon has two methyl group. I have shown them like this, and a negative charge will develop on this oxygen. Now it can exist for some time because negative charge is purely on oxygen, and this is a stable negative charge. And then this will neutralize when you add water into it. Later, when you will be adding water, because water is coming out already, so this molecule that has came out, this can give its proton to this oxygen, and that's how this O minus will turn into OH. Fine. So this is the final product if you don't provide heat. As you can see, this is a keto form. Historically, the name has been given aldol. Even if you're getting a ketonic group, we don't call it ketol. Even if it is ketol, even if you're getting a ketol, still the name of the reaction is aldol. Fine. This is a ketonic group because you're having carbon on both the side of C double bond O. So this is not an aldehydic group. This is an alcoholic group, but this is not an aldehydic group. But still the name of the reaction is aldol condensation. The name is not ketol condensation. Anyway, but that's how the name, because you are getting suppose this was an aldehyde, then you are getting an aldehyde and you are getting an alcohol as a product of this reaction. So this is the name aldol condensation. The condensation hasn't come yet. Up till now we have just produced aldol. Fine. Now, if you heat it, if you don't provide heat, the reaction will stop here. But if you heat it, then on heating, what happens, we have discussed before. On heating, the energy of the substrate, of the substance that you have taken increases. On increased energy, the motion of electronic wave increases, and then something happens. Anything can happen. Generally, a small molecule leaves the substrate, and that is called condensation. What happens here is this hydrogen and this OH group comes out. Water is removed off. When water goes off, this carbon loses one bond, this carbon loses one bond, and then both will form one bond each. So a C double bond C is going to appear at this position. So after condensation, what you are going to get is alpha, beta, unsaturated carbonyl compound. This is the alpha position of this carbonyl and this is the beta position, and at alpha and beta you are having unsaturation. So this is alpha beta unsaturated carbonyl compound. So this is the final product of aldol condensation. You started with a carbonyl compound and you are ending with a alpha beta unsaturated carbonyl compound.